My name is Jack Hollick, and this is Lab 3, Black Hole, for Physics 2211. As a brief introduction, the purpose of this lab was to determine the mass of a black hole when given the mass of a star that was orbiting the black hole and the randomized trajectory of the object's or the star's orbit. We then used this mass to find a reasonable velocity with which a spacecraft could leave a planet that is also orbiting the black hole without crashing into the black hole or the surface of the planet. Finally, we ended up finding out that the mass of the black hole was approximately 1.19 times 10 to the 34 kilograms, and, when this is the case, that the spacecraft could avoid collision with the black hole and the planet when its initial velocity was negative 4.7 times 10 to the 7 in the x direction and 4.7 times 10 to the 6 in the y direction, meters per second. In part 1 of this lab, there are a few physics principles that are necessary to comprehend. First is momentum, where momentum is equal to mass times velocity. Next, it is important to note that the Greek letter delta represents change, and therefore, in the momentum principle, where F net equals dp over dt, the net force is essentially equal to change in momentum divided by the change in time. And finally, in circular motion, there are two components. The parallel component, which changes the speed of an object. It involves p hat, which is found when you divide the momentum by the magnitude of the momentum, and essentially the parallel component is equal to that p hat times the change in magnitude of the momentum divided by the change in time. Second, there's a perpendicular component, which changes the direction of the object, which is essentially equal to the net force of the object acting on the object minus the net force in the parallel direction. The second portion of this physics lab also has some very important concepts. The first is how circular motion relates to gravitational force. The centripetal force of mv squared over r is equal to the gravitational force of gmm over r squared, so v can be rewritten to be expressed as the square root of gm over r. The gravitational force, in addition, can be calculated with the equation gmm over r squared times r divided by the magnitude of r, where r divided by the magnitude of r is r hat, and r is simply the position or the distance between the two objects. The sum of the forces is equal to the net force, so every component of every force acting on the object sum to get the net force. The velocity update formula in the case where F net is not constant can be given final velocity equals initial velocity plus acceleration times time, or initial velocity plus F net over m times t. In addition, the position update formula when F net is not constant can be written to say the final position equals the initial position plus velocity times time, where velocity is equal to the final velocity of the previous final velocity update formula, and it is calculated in iteration throughout the trajectory of the object, so that the velocity given is reflective of the velocity of the object at every time interval throughout its trajectory when the net force is not constant. For part 1, finding the mass of the black hole, the initial conditions of the star was that its mass was 2.0 times 10 to the 30th kilograms, and that it had a momentum I will show later in my code. For part 1, we have the star's mass is listed here. The time interval is 86,400 seconds because that are how many seconds are in a day. We have the momentum and velocity components of the star at various times, and we use those to determine the net force acting on the star in both the parallel and perpendicular directions, and from that we can find the mass of the black hole. Here we take the average of all the masses we find to get one average value. The net force differs from the rate of change of momentum because the rate of change of momentum is the result of the net force. When we observe an object in motion, the result of the motion is because of a rate of change of momentum, and the cause of that change of that motion is because of the net force, whether it be in the parallel and or perpendicular directions. When there is a net force acting on an object, the result of that net force is a change in the rate of momentum. To this lab, don't crash. There is a spaceship that is located on a planet closer to the black hole than the star from part 1. The ship launches from the side of the planet that is facing the direction of the velocity. The system is the spaceship, and the surroundings are the black hole and the planet. The code for part 2 is shown here, with the mass of the black hole found from part 1 listed here, and the time it takes the planet to orbit the black hole one time listed here. The speed of the ship in both the x and y direction is given here, which is a result of these equations that were derived to determine the net force on the planet and on the spaceship. Finally, to calculate the correct iterations of motion, the ship's velocity and position were updated here, and this ultimately allowed us to go back to this speed and determine what was appropriate so that the space shuttle would not crash. The best guess as to how to get the ship into orbit of the black hole would be to have the ship launch at an angle theta, where t cosine theta, where t is equal to the thrust force, is non-zero, so the ship does not have the same trajectory as the planet once in orbit, and also where t sine theta, the y component of the velocity, is great enough so that it can leave the atmosphere of the planet. In conclusion, we found the mass of the black hole, even though we were only given the mass of a body in orbit of the black hole and the velocity of that body. And in part 2, we found the initial speed of the spacecraft so that it could leave the orbit of one body while maintaining orbit with another body. One potential error is that if part 1 is wrong, part 2 is also likely wrong. The end.